Hello everyone, this is Sinu. I am from Sri Venkateshwara College of Engineering. Today we will discuss about what is automata, what is NFA, what is TFA, and conversion from the NFA to DFA, and that steps. What is automata? The word automata comes from the Greek word that means self-acting, self-willed, self-moving, and automaton and abstract self-propelled computing devices, which are followed by the predetermined sequence of operation automatically. An automaton which a finite number of states is called a finite automaton. Formula definition of a finite automaton. An automaton can be represented by the five tuples that can q summation delta q naught f, where q is a finite set of states. Summation is the finite set of symbols called the alphabet of the automaton. Delta is a transition function. Q naught is the initial state from the where any input processed of Q naught epsilon closer Q. F is the set of final state of a states of a Q of a F less than equals to Q. What is NFA theory in automata? Non-deterministic finite automata. In a non-deterministic finite automaton, for each state there can be 0, 1, 2 or more transition corresponding to a particular symbol. If NFA gets the states with a more than one possible transition corresponding to a input symbols, we say that branches. What is NFA for regular language? NFA is a state machine used to validate an input string using the transition. Regular expression are a sequence of characters that are used to the checker given to the string allows the pattern not, patterner or not. Both NFA and regular expression can be used to the deterministic regular language. What is TFA? Deterministic finite automata are finite states machine that can accept rejected strings of characters by parsing them through a sequence that are uniquely deterministic by each string. The term deterministic refers to the fact that each strings that can be state sequence of is unique. In practice, TFS are made up a given five components. We are seeing the first slide. These components includes a finite number of states, a set of symbols known as alphabets, also finite numbers, the functions that operators the transition between the states of each symbols, an initial start state where the first input given to the processor, a final state or states known as accepting states. Example of this diagram: the step 1 converted to the NFA to DFA. To convert the NFA to its equivalent transition table, we need to the list of all the states, input symbols, and the transition rules. The transition rules are represented in the form of a matrix where the rows represent the current state, the columns represent the input symbols, and the cells present the next state. The step 2, create the DFA start state. The DFA start state is the set of all the possible starting states in a DNFA. In set is called as a epsilon closer of the NFA start state. The epsilon closer is the set of all states can be reached from the start state by following epsilon transition. The steps 3. Create the DFA transition table. The DFA's transition table is similar to the NFA transition table, but instead of individual state, the row and columns represent the set of states. For each input symbol, the corresponding cells to the transition table contains the epsilon closure of the set of states obtained by the following transition rules in NFA's transition table. The step 4, create a DFA's final state. The DFA final states are a set of states that contains at least one final state from the NFA. The step 5, simplify to DFA. The DFA obtained in the previous steps may contain unnecessary states and transition. The simplified DFA, we can use the following techniques. Remove, remove unreachable states. States that cannot be reached from the start state can be removed from the DFA. Remove dead states. States that cannot lead to a final state can be removed from the DFA. Merge equivalent state. State that can have same transition rules for all input symbols cannot be merged into a single state. Step 6. Repeat steps 3 to 5 until no further simplification of a possible. After simplifying the DFA, we repeat step 3 to 5 until the further simplification is possible. The final DFA obtained from the minimized DFA equivalent to the given NFA. Next, we are seeing the conversion of the NFA to DFA problem. Transition table for the given non-deterministic finite automata is it is a Q naught is given to 0, it is moved to the Q naught. It is moved to the Q naught. Q naught, it is given to the 1, it is moved to the Q1 and Q2. It is Q1, it is given to the 0, Q1, it is moved to the 0 and 1 also. It is moving to the Q2 and Q2 is returnly moving to the 1 of Q1 and Q2 is a final state. Q2 is moving to the Q2 is moving to the Q1 and Q2. Let Q be a new state of the states of the DFA. Let T be a new transition table from DFA. Add transition of the table Q0 to the transition table T. New state present in a Q is a new state is a Q1 and Q2. Step 4. We state present in a state Q is a Q0, Q1, Q2. Table Q0 is a starting state and it is moved to the 0 of a Q0 and Q0 it is moving to the 1 of Q1 and Q2. We now consider the Q1 and Q2 is a final state. It is moved to the 0 of Q0, Q1, Q2. Then it is moved to the 1 of a Q1 and Q2. Step 5. It is converted to the DFA table. And state is a Q0. Q0 is moving to the 0 of Q0 and Q0 it is moving to the 1 also and final state of a Q1 and Q2. It is considered the state of a Q1 and Q2. It is moving to the 0 of a Q0, Q1, Q2. It is moving to the 1 of a Q1 and Q2. We now consider the state of a Q0, Q1, Q2. It is transition of the 0, Q1, Q2, Q0, Q1, Q2. It is moving to the 1 of the Q1 and Q2. Now, DFA may be drawn in as final diagram. It is here Q0 starting state. It is a self loop also. It is given to the 0. It is 1 moving to the Q1 and Q2. And it is moving to the 0 of a Q0, Q1, Q2. It is also final state and it is given to the self loop as 0. It is returned to the Q1, Q2 as 1. Thank you for watching my video.